Biomaterials. A biomaterial is any natural or man-made material that can be accepted into the body for medical use. They are systematically, pharmacologically inert high-tech materials used to make devices to replace functions of living tissues or organs in a safe, reliable, economic, and physiologically acceptable manner. This presentation about biomaterial is intended to be an educational resource only. Biomaterials and its characteristics. Biomaterials are biocompatible, biofunctional, bioinert, biotolerant, bioactive, biodegradable, bioresorbable, and they exhibit bioerosion and bioabsorption. Biocompatibility. It is the ability of a material to perform within a suitable host response in a specific application. It should be non-toxic, carcinogenic, non-allergic, non-teratogenic, non-immunogenic. Non-teratogenic cause no birth defects. Non-immunogenic cause no immune rejection. Examples. Titanium and titanium alloys are the best examples. Titanium integrates into bone perfectly. Outermost titanium atoms in contact with body fluids capture oxygen. And oxidizes. The first layer, it undergoes oxidation and then it cannot alter its bonding to the second layer. They remain stable in position and bind to the next layer. Hence, no ionized atom is detached. Bone tissues repair their injuries without perceiving the aggressor. It has high strength, low modulus. It is strong and corrosion resistant. Applications. Titanium screws are used for dental implants. This is the titanium screw. It is also used in cardiovascular system. Biofunctionality. Functionality exhibited by a biomaterial corresponding to a biological function at certain period. Examples are titanium and stainless steel. Applications. Load bearing is one example of application. Titanium implants bear load due to its density and elastic modulus near to bone. In case of knee joints, titanium is used for tibial tray, and for femoral component, titanium alloy is used. In case of hip joints, acetabular shell is made up of titanium alloy and femoral stem is also made up of titanium alloy. Bone plates of titanium are used in the case of fracture of bone. Applications. Stress bearing is one example of its application. Stainless steel inside the body bears stress. It is used for fracture plate. This is fracture plate. And also it is used for fracture nails. Self-stepping leg screw is this. Distal bolt is this. Applications. Dental filling. Mercury amalgamated with silver, copper, tin fills up the gap in tooth as it quickly adapts the shape of the teeth. Fluid flow control is another example of biofunctionality. It is for stimulating physiological function. Generation of electric stimuli and transmission of light and sound, etc. is also another example of biofunctionality. Bioinert materials. They do not bond to bone, but make contact without chemical reaction and maintain their physical and mechanical properties while in host. They are non-biodegradable. They are corrosion resistant and wear resistant. They are mechanically tough and do not enhance an immune response. Examples are alumina, zirconia, and carbon. Metal examples are titanium alloys, and 316 stainless steel. Polymer examples are polyethylene. Application of alumina implants. Alumina is used for femoral head. Then it is used for dental bridge, for bone screws and plates, and for bone grafts and scaffolds. Applications of zirconia, alumina, and zirconia tough and alumina. In short, ZTA. Zirconia is used as a bone cement. It fixes implants, reduces operation recovery time, bears load, and offers stability. It is also used in case of dental implants. It is more cosmetic, prevents gum disease, and suitable for thinner gum tissue. Alumina, zirconia tough and alumina are used for ceramic femoral heads. They are scratch resistant, wear loss, much harder, stronger, and smoother. Polyethylene. It is used for acetabular cup, and this is polymeric cup. Also, it is used as an spacer in between the tibial tray and femoral component. Biotolerability. Biotolerant materials do not integrate into bone and get separated by a thin fibrous tissue interface. They are corrosion resistant and stronger. Examples are alumina, zirconium, cobalt chromium alloys, 316L stainless steel. Polymer examples are polyamide, polymethyl methacrylate, polytetrafluoroethylene. Applications. Gold is used for dental casting and for dental bridge. Dental casting lasts for patient's lifetime. It is biocompatible. It possesses high durability and it is more cosmetic. Stainless steel is used for internal fixation in bone supporting. Bioactivity. It is an activity exhibited by a biomaterial to connect with a bone tissue. Bioactive materials chemically bond to bone, and this is called osseointegration. Bioactive glass is one example of bioactivity. It was invented by Larry Hans in 1969. It has calcium, phosphorus, silicon, and sodium oxide, similar to a living human bone. When it is in contact with biological fluid, it releases sodium and calcium ions. It loses silica as silicon oxide. Calcium and phosphate ions migrate to the glass surface and form amorphous calcium phosphate layer. Uptake of anions, that is OH ions and carbonate ions, from the solution into the calcium phosphate layer converts it into hydroxyl carbonate apatite layer. Osteoblast cells on this calcium phosphate rich surface layer are attached. Crystallization of calcium phosphate to form HCl layer is shown in the figure. Bioactive glass applications. It exists as particulates as bioactive synthetic bone graft from Nova bone. Synthetic bone graft particulate of size 90 to 710 micrometer from perioglass. Then glass cones of different sizes has been developed by Dr. MN. Bioglass particulates having the size less than 5 micrometer are used in toothpaste like Novamine Corp, Biomine, and Sensodyne Repair and Protect. Synthetic bone graft particulates are used for bone grafting and bone filling. They restore bone loss due to holes in jawbone. They are mixed with patient's blood and pushed into the defect as putty. Bioglass middle-ear device replaces middle-ear bones and restores hearing loss. Particulate. Bioglass particulate in toothpaste fill in areas of damaged enamel and forms HCl layer. Particulates dissolve in enamel and release calcium and phosphate ions, thereby relieving the pain. Bioactive glass scaffold. It acts as framework and guide for bone regenerative cell in a large bone defect. Its pores are identical to those in human bone. It is better for synthetic bone graft. The pore network is interconnected and allows continuous tissue ingrowth. It is relatively brittle and survives in low load size, just like in shoulder bone defect. 3D printing. First, patient's CT scan is done. Secondly, we have to isolate 3D model from CT scan using 3D printing. A scaffold or implant with accurate size is 3D printed. and thus bone grafting is completed. Biodegradability. Biodegradable materials get degraded into smaller molecular weight macromolecules and may not be completely eliminated but may stay inside the body or migrate. Examples are biodegradable polymers. They are classified as natural polymers and synthetic polymers. Natural polymers are fibrin, collagen, gelatin, chitosan, and hyaluronic acid. On the other hand, synthetic polymers are polyglycolic acid, polylactic acid, PGA-PLA copolymer, and polyanhydride. Applications of natural polymers. Fibrin is used as tissue adhesive. Collagen and gelatin are used for wound dressing and for bone void filling. Collagen cream is used for hydrated skin. Hyaluronic acid is used as lubricant in bone joints, and it is also used as super hydrating face masks, which can moisturize, smoothen, and tighten the skin for yacht looking. Chitosan is used for wound healing, drug delivery, and tissue engineering. Synthetic polymer applications. PGA is used for fast biodegradable sutures. PLA is used for interference screws, which are used for plastic surgeries. It is stable and hydrolyzed by water from tissues and replaced by bone. Porous scaffolds are used for drug incorporation. Then vascular graft is used for healthy blood flow. Then biodegradable screws are used for medical use. Bioresorbability. Bioresorbable materials get resorbed into very low molecular weight molecules in vivo and get eliminated and not stay inside. Examples are metals, polymers, and bioresorbable polymers, natural polymers, and synthetic biopolyesters. Examples are PLDL, PLGA, PLCL, PCl, PDO, PLTMC, and PDLLA. Inorganic compounds have less dissolution, high chemical stability. Silicon nitride possesses chemical stability, high resistance, and low friction. Manganese oxide attracts attention due to their properties. Bioresorbability applications. Metals are used for bioresorbable stents, which is implanted in blood vessels. Stent is left in place. PLA, PDLLA, PLGA are used for suture anchors, interference screws, and sutures. Suture anchors are placed in bone to attach the sutures for holding the soft tissues. PDLLA is used for craniomaxillofacial. PCl is used for 3D printed scaffolding, 3D printed long-term regenerative bone implants, controlled drug release. inorganic compounds protect bioresorbable implants. Silicon oxide is used for drug delivery, pharmamedical, and natural product. Bioerosion. Materials get degraded on surface and resorbed in vivo. In surface erosion, the materials get thinner uniformly with time and device is thinning. In bulk erosion, the materials may break into pieces inside. Bioabsorption. The materials get dissolved in the body with no change of their molecular weight. Chemical stability. It means resistance to biological aging. Machinability. The material can be molded and disinfected. And sterilizable. A biomaterial is sterilizable. Sterilization eliminates impurities and microorganisms before implantation. Lastly, we discuss about biomaterials generations. Since the middle of the last century, biomaterials have evolved exponentially and can be divided into 4 generations. The first generation biomaterials appeared nearby 1960 to 70. They are bioinert. The second generation biomaterials appeared between 1980 and 2000. They are bioactive, bioresorbable, and biodegradable. The third generation biomaterials appeared from 2000s onward. They are bioactive as well as bioresorbable and stimulate specific cellular activity at molecular level and regenerate functional tissue. Fourth generation biomaterials appeared in the last decade. They can manipulate cellular bioelectric signals to regenerate tissue and monitor cellular responses and allow for communication with host tissues using bioelectric signals. The next generation biomaterials will be increasingly influenced by advances in cell and molecular biology, and that the combination of these electronic biomaterials with biosensors, new drug delivery systems, and tissue scaffolds will boost the development and clinical application of new medical devices. Thank you for watching.